Well, we've reached the halfway point of Chapter 4. We're here in Section 4.4, as you can see, Properties of Rational Functions. We're going to be talking today about specifically the domain of a rational function, the finding the vertical and horizontal asymptotes of a rational function, and that's where we're going to kind of camp out today. But before we start that, I want to talk a little bit about rational expressions and what we've learned in the past. We've seen rational expressions in the form of, let's say, like x squared minus 4 over x plus 2, and you factor the numerator and canceled. You've seen these different kinds of rational expressions: 3x minus 1 over x cubed, or x to the fourth over x minus 1. So these are all examples of rational expressions where you have a polynomial divided by a polynomial. And so we're still going to be hearing about polynomials, but again, we'll get into the definition of a rational function here in a minute. I also want to talk a little bit about graphing rational functions. So let's get rid of this here. We look at the basic rational function of y equals 1 over x. We know that 1 over x, at least we should know that 1 over x looks like this. Okay, it's a hyperbola there, and anyway, we've dealt with these kinds of functions before, and we've even dealt with their transformations, like let's say y equals 1 over x minus 2, and with a little bit of thought behind that, you could realize that, hey, I need to take this graph here of y equals 1 over x, and I'm going to shift it to the right 2 units. Okay, so we can see, hopefully we can see clearly that we have a vertical asymptote at x equals 0, and if everything on the graph of 1 over x shifts over 2 units to the right, then even that vertical asymptote will shift over, and then we can just draw the same graph. Remember, when we're using transformations to graph functions, the shape of the function doesn't change, it's just the position of the function changes. Okay, so that's a little bit about the graph of y equals 1 over x. These concepts are going to come in really handy in this section because we're going to have to actually graph these rational functions, and knowing the general shape of the graph is really important, but also the behavior of rational functions. Many times in rational functions we'll have both a vertical asymptote and a horizontal asymptote as well, and even though it doesn't look like we have a horizontal asymptote, the actual x-axis is in fact a horizontal asymptote for both of these graphs, and as you can see and we talked about, there also is a vertical asymptote. I wanted to give you the definition of a rational function and help you see. Here we have we can see we have a polynomial function divided by a polynomial function. Both p of x and q of x are polynomials, and that's what it says here. But also q is not the zero polynomial. All that means is that the degree of the denominator must be 1 or higher. So degree must be greater than or equal to 1. So we know, we talked about polynomial functions. We know that x to the 0 power would be a 0 degree polynomial, and that would just be a constant. So anyway, the degree must be greater than or equal to 1. And the domain, we're going to talk about that here. The domain is all real numbers except for those real numbers in which the denominator is 0. So we've actually already worked on and looked at rational functions, and we've even called them rational functions. But here we're going to be putting all the concepts together and discussing more in detail the specifics of rational functions. So let's go ahead and do that. We're going to find the domain of a rational function. And again, just to reiterate, we've done this before. If x plus 5 is in our denominator, whether we can cancel it or not, whatever makes the denominator 0, x plus 5 equaling 0, so x plus 5 is not allowed to equal 0, and so the domain is all real numbers x such that x cannot equal negative 5, because you have to subtract 5 from both sides here, so x cannot equal negative 5. Same thing over here for part B. X squared minus 4, when that is equal to 0, we see that x is equal to negative 2 and positive 2, so we see that the domain is all real numbers except for those two, 2 and negative 2. Okay, and let me put a nice box around that. I didn't want to cover up that next part here though, so let me see if I can be a little bit more careful. Alright, and the last one, this one tends to trick students sometimes, but because they see a denominator, they think, oh, automatically there's a value for x that would make that denominator equal to 0, but in fact x squared plus 1 is always greater than 0, therefore the domain is all real numbers. Therefore all real numbers is the domain, and just to maybe help you see it a little bit better, think about values of x. Okay, so if you picture x being positive, then there's no problem. If x is 0, then 0 squared is 0, and plus 1 is still going to be positive. And then if we square any negative number, we're going to get a positive number. So actually the lowest that this denominator can be would be 1, and so it's definitely greater than or equal to 1, which is obviously greater than 0. So therefore all real numbers is the domain. So pause the video and try this next one on your own. And I'm going to go ahead and show you the solution. We've got g of x equaling this function. X minus 2 cannot equal 0. Okay, even though I know I can multiply or factor out this numerator and cancel, I do know though that x minus 2 cannot equal 0, so therefore x cannot equal 2. So all values of x such that x cannot equal 2, and there is our domain. Okay, let's move on. Go ahead and pause the video and write this function down, y equals 1 over x squared. And we're going to be analyzing the graph y equals 1 over x squared. First by looking at a chart and then looking at the graph itself. So let's take a look at this chart. When we make an xy chart, we make it look a little bit different than what you see here. So our xy chart really looks like this. So we're picking inputs, and then we're replacing the x with those inputs. So if we took x and replaced it with 1/2, think about that. 1 divided by 1/2 quantity squared would be 1 divided by 1/4, which is really 1 times 4. Okay, so that's why we get a 4 here. Okay, we can see that when the input is 1/10, oh, sorry, by the way, 1/2 comma 4 would be that point right there on the graph, so that those coordinates correspond to a point on the graph of this function. Okay, and then again when we replace x with 1/10, we see that we get 1 divided by 1/10 quantity squared, and with the same kind of reasoning we can see we get 1 divided by 1 over 100, and therefore we get 100. Okay, so the bottom line is this: as x is getting closer and closer to 0 from the right hand side, so 1/2, 1/10, we can see that the values of y, the values of the function, are getting really big. Okay, and then as x gets bigger in the positive direction, we've got when x equals 1, y equals 1, x equals 2, y equals 1/4. So the y values are actually getting smaller as x is getting bigger, and that's why the right side of the graph looks the way it does. So we've got the right side of the graph, or I should say in the first quadrant, the right side of the y-axis, we see that the graph looks like that, because as x gets bigger in the positive direction, the y values get smaller, and as x gets smaller from the positive side, the y values get bigger. Okay. And by the way, as you can see from the left side, or on the left side, if we replaced each one of these inputs with a negative, the opposite of what they were before, we're still going to get the same outputs. Okay, so that's why you see the corresponding points on both sides of the y-axis, and that's why that happens, and that's why the graph of 1 over x squared looks the way it does, because of the behavior of the function for the different inputs. Okay, so we all know how to graph functions. Let's go ahead and try another one. So here's the next one. I want you to go ahead and pause the video. Since you already know what the graph of 1 over x squared looks like, you should be able to take that graph and shift it to the right 2 units and up 1. But anyway, go ahead and pause the video. I'm going to go ahead and play. Okay, we start with 1 over x squared, like that, and then we're going to shift to the right 2 units. Replace x by x minus 2, shift to the right 2 units, and then that plus 1 at the end means that we're just going to add 1 to every y value, and in essence shifting the graph, the second graph here, up 1 unit to get the final graph of the function that we're trying to graph. Okay, so let's see what else we've got. So this one, I want to camp out on this one a little bit. It might look a little scary. I don't necessarily want you to copy this down. I just want you to kind of watch. Okay, let's look at this first graph here, the first chart, in which basically, again, we see an XY chart. Okay, R of X is defined up here. Okay, and in the XY chart, we see we're choosing bigger and bigger values for X and seeing what in the world is going on with the function. So as we pick larger values for X, we can see that the function is getting closer and closer to 1. Okay, so as X approaches, you think about this, as X approaches infinity, the Y values are approaching 1. Okay, well that's fine. And then let's look over here in the chart for part B. As X is approaching, you should be seeing here that X is approaching negative infinity. Let me erase this guy here. Okay, so X again is approaching negative infinity because the negative values are getting really, really big. Okay, what's going on with the value of the function? 1.0069, and then getting closer and closer to 1, just like the way it did in the last chart. Okay, and we're going to talk about what that means. All right. And then over here we've got another chart in which we see X approaching the number 2, okay, but from the left, okay, right, 1.5, 1.9, 1.999, 1.999, right, so we're getting closer and closer to 2 from the left. And where are the Y values going as X gets really close to 2 from the left? Well, you can see the Y values are getting huge. The Y values are going towards infinity. Okay, same with when we approach 2 from the right hand side, from values of X that are greater than 2. That way we can tell what the behavior of the graph is. So as X is approaching 2 from the right, where are the Y values going? Well, the Y values are going towards positive infinity. Just like when you were approaching 2 from the left hand side of 2. Okay, so let's look and see what that represents. So here is the complicated way of, well, maybe the last little segment there was probably pretty complicated. I know I'm doing a lot of talking, but I'm trying to give you the background here, and you can always go back and take a look. But the bottom line is this. As X gets really, really big in the positive or the negative direction, and the function's values are approaching a real number that is not infinity, okay? So some real number, any real number less than infinity. If the Y values are approaching that real number, then we say that Y equals L is a horizontal asymptote. Okay, horizontal asymptote. So likewise, if X is approaching, we already know about the horizontal asymptote, but as X is approaching some value C, okay, so here's some random real number. If X is approaching that value C, you can see X equals C up here, that vertical line. But as X is getting closer and closer to this C from both sides, we say that if the value of the function is going towards either positive or negative infinity, then the line X equals C is what we call a vertical asymptote of the graph of R. The graph of R never intersects a vertical asymptote. It can, by the way, intersect a horizontal asymptote, but never can the graph of F, or whatever function it is, ever intersect a vertical asymptote. Okay, so notice here that as the Y values get bigger and bigger, that's where the Y values are approaching infinity. Okay, so if the Y values are getting bigger and bigger from either side, we say that the Y values are approaching infinity. And infinity, again, is just a concept, it's not a number, so the Y values just keep getting higher and higher. So if we look at the behavior of the graph near the vertical asymptote, we can see clearly that either the ends could go together, the ends of the graph, towards the vertical asymptote, or you can have from one side moving way up and then the other side moving way down. Either way, you don't even need this guy here. You don't need, oops, come on, give me my eraser. There, why is it not erasing? It's not behaving well. Okay, well, again, you actually don't even need this guy right here. If you just had the y values getting bigger from one side as x was approaching that x value, c that we called it, then we would say that x equals c is a vertical asymptote.